Good morning everyone. Welcome to session 1 of day 8. We start talking about some of the research problems in cybersecurity, a very limited set of problems, and some of the things that we are doing here in this department at IIT Bombay. So I'll just straight away go to, so there were a couple of questions by the audience. Can you discuss elliptic curve cryptography? Can you introduce it and talk about some of it? So this is a rather ambitious task today, to actually introduce elliptic curve cryptography and then look at some of the research that we have done, some very interesting research problems on optimizing what's called scalar multiplication in ECC. So before we get to the heart of this problem, let us just introduce ECC. So what are elliptic curves? We consider elliptic curves over 3 different fields. So we define briefly what was a field. If I have to talk about fields in great detail, it will take several lectures. So what I did was to summarize or very briefly introduce the idea of a field, and before that the idea of a group. So if I were to recall the definition of a field has got a set. The set can be a finite set, it can be an infinite set, and then there are 2 operators, the generic plus operator and the generic multiply operator. In a nutshell, the field, the set of elements together with the generic plus operator constitutes a group. And as mentioned, there are 4 group properties, namely closure, associativity, the existence of an identity, and the inverse. So once again, the set of elements in the field together with the generic plus operator constitutes a group. Also, the elements in the field minus the additive identity, so exclude the additive identity, and that set together with the generic multiply operator again constitutes a group. We call that the multiplicative group of the field, and the earlier group is referred to as the additive group of the field. And then there is also the property of distributivity that I mentioned some lectures ago. Now the 3 fields that are of importance to us, actually there are 2 fields of importance, and one is this field that is actually a well-known field, the field of real numbers, which includes the operators, the simple arithmetic operator plus an arithmetic operator multiply. So this is the field of reals, which everybody is familiar with in school days also. And then the 2 fields that are of interest to us, the 2 finite fields, are the prime field and the binary field. So the prime field is nothing else but, say you choose a prime number p, let's say p is equal to 7, and all the integers 0, 1, 2, 3, 4 right up to 6, with the operators being addition modulo 7 and multiplication modulo 7. So that is another set of fields besides the real numbers, and then binary fields. So I won't get into the details of binary fields because it's a little, it's a little time consuming to deal with all the operations and so on. I briefly mentioned binary fields in the context of AES some lectures ago. So we will look at what are the operations in each of these fields, what are the elliptic curve operations in each of these fields, and even before that, what is an elliptic curve, the equation of an elliptic curve. So elliptic curve over reals includes all points that satisfy this equation. So the elements x, y, and even the coefficients a and b are all elements of the real numbers. We refer to such a field that satisfies and respects this equation, we refer to such a graph as an elliptic curve over reals. We say over reals because these coordinates and these coefficients a and b are real numbers. The constraint is that 4a cubed plus 27b squared should not be equal to 0. So this is the equation of the elliptic curve. You are given the coefficients a and b, and then figure out what are the x and y that satisfy this and plot that. That is the elliptic curve. It's interesting that the elliptic curve also includes the so-called point at infinity, which we designate as something like an O. This is not 0, this is actually the point at infinity, but as we will soon see, this element of the elliptic curve is actually the identity of the elliptic curve group. So I'll just come to that in a second. Just note at this time that there is a very special point. This is not the point with coordinates 0, 0 or anything like that. This is an abstract point, the so-called point at infinity, which is also part of the elliptic curve. So here is an example of a curve. You can plot it out yourself. The curve y square is equal to x cube minus 5x plus 8. I think some of my students plotted this in an Excel sheet. So this is what the curve looks like. Interestingly enough, I changed the coordinates a little bit and the curve looks completely different. It looks like it's got two different pieces out here. So once again, this is an elliptic curve over real numbers, and there are an infinite number of points on this curve. Now once we define the curve and we understand what it looks like and so on, the next thing is, what are the operations on this curve? So we are talking about curve operations. The first is what's referred to as unary negation. Unary as opposed to binary. Unary negation, there is just one operand. So if the coordinates of P are x and y, then minus P, the unary negative of P, has coordinates x and minus y. So that's the first thing, unary negation. The next thing is that we need to define is point addition. I'd like to add 2 points on the elliptic curve P and Q. Let's suppose that the coordinates of P are x1, y1 and the coordinates of 2 are x2, y2. Then what are the coordinates of the sum of P and Q? Let's say those coordinates are x3, y3. Then what is the expression for x3 in terms of x1, y1, x2, y2? What is the expression for y3 in terms of x1, y1, x2, y2? So we need to derive that, but first there's a nice geometrical interpretation for the addition of 2 points in the curve. So to add 2 points, draw a straight line connecting them. Let the third point of intersection between this line and the elliptic curve be x3 comma minus y3. Then the unary negative of this is actually the point that we are interested in, which is x3 comma y3. This is the sum of P and Q. So let's just look at this. There are some degenerate cases which are handled separately, but just let's look at the most important cases first. So here's an example. I'm adding 2 points A and B. Now what should I do? Join them with a simple straight line segment and extend that line segment until it hopefully hits the curve at a third point. So almost always it will, but occasionally one of them is a tangent and so on and so forth, so it may not hit the curve at a third point. But those are degenerate cases. For the time being, let's talk about the normal case. I connect A and B and it hits the curve at this point, which is actually minus C. So I need to find the negative of this point to obtain the sum of A and B. And the negative of a point, as mentioned on the previous slide, is if the coordinates are x, y, then the negative of that point is take the same x coordinate, but take the y coordinate and take the negative of that y coordinate. That's the mirror image along the x-axis. So I join these two A and B, it hits the curve at a third point, and then I take the mirror image along the x-axis. So that gives me this thing. So if this coordinate is x3, y3, then this is x3 comma minus y3. So this is a geometrical interpretation of the addition of 2 points on the elliptic curve. So this is the elliptic curve over reals, that is over real numbers, over the real field. These are 2 arbitrary points I've just chosen. I want to add them. I connect them. I see where it intersects the curve at this third point. And then I take the mirror image and I get the sum of A and B, which is this point. So A plus B is equal to this thing. Now you can actually go through some equations. It is all in the textbook to find out what are the coordinates of R, the sum of P and Q. So if the P is x1, y1, coordinates of Q are x2, y2, coordinates of R are x3, y3, then you can express x3 and y3 in terms of these things, these known things. So x3 is s square minus x1 minus x2, and y3 is minus y1 plus s times x1 minus x3, where s is the slope, and from your high school mathematics coordinate geometry, you know how to find out the slope of a line connecting 2 points x1, y1 and x2, y2. The slope is y2 minus y1 divided by x2 minus x1. So this s over here is nothing else but the slope of the line segment connecting this point and this point. Okay, so we talked about unary negation. The next thing is point addition, and the third thing is doubling of a point. So to double a point P, again there's a nice geometric interpretation for this. To double a point P, draw a tangent at P. Let the coordinates of the point of intersection between the tangent and the elliptic curve be x2 minus y2. Then the twice point P, the coordinates of that point are x2 comma y2. let's look at a geometrical interpretation. So I want to double this point. So before I ask the question, what is A plus B? Now I'm asking the question, what is A plus A? So that is twice A. So what I do is, I draw a tangent at this point, and hopefully it's going to hit the curve at some place. So at this point, for example, and this point, then I have to take the mirror image as usual, and that is twice of this. So you can think of it as adding A to itself. A and A are next door to each other, basically the same point. I take a line segment connecting them, basically a tangent at that point, and I see where it intersects the elliptic curve, and the mirror image of that point is twice of A. So these are the three important operations as far as cryptography and security are concerned, that is unary negation, point addition, and point doubling. So please remember these three things: unary negation, point addition, and point doubling. So if I'm talking about unary negation, if I take any point on the elliptic curve, then the negative of that point is simply the mirror image along the x-axis, would be this point. If I'm talking about adding 2 points, A and B, then I see where it intersects the elliptic curve, and I take the negative of that point, that's A plus B. And when I want to double a point, I just draw the tangent at that point to the curve, see where it hits the elliptic curve, and then take the negative of that point. So these are the three fundamental curve operations. Just like we wrote down the coordinates of P plus Q, here are the coordinates of the point 2P. The coordinates of the point 2P, x2 and y2, are expressed as in terms of the coordinates of the point P. The coordinates of the point P are x1, y1, and these are the expressions for x2 and y2. Now we don't want to learn any of this by heart, we just want to understand basically what is going on and to be able to use these equations to do encryption, decryption, signatures, key exchange, and so on and so forth. So elliptic curve cryptography is now one of the hot items in crypto. Many of your browsers, or probably all of them, will support ECC. So this is the new thing that is likely to replace RSA in the days to come, because it is computationally more efficient and likely to be also more secure. So having defined these operations, the next very important statement is that the points on the elliptic curve form a group. So we know what is a group. Once again, a group is a set together with an operator and the four properties, namely closure, associativity, the existence of an identity in the group, and the existence of an inverse for each point. So when we say the elliptic curve points form a group, then we of course ask ourselves what is the operator, and the operator is the plus, that is the addition of 2 points in the group. So when I make a statement that the elliptic curve points form a group, then the question is, what is the set? The set is the points on the EC which satisfy those equations that I mentioned before. Y square is equal to x cube plus ax plus b. So those are the points on the EC. So that is the set in this group. And then the operator. The operator is simply the plus operator, that is the addition of 2 points, which is defined in the previous slides both geometrically and through those equations. This is the group operator. If I've got 2 elements in the group, then the sum of those 2 elements is given by R, the coordinates are given by these 2 things. So this important statement that the EC points form a group. Now if they form a group, the next question is the discrete log problem feasible on this group or not? Fortunately, it turns out that for carefully chosen groups, the elliptic curve discrete log problem is infeasible. I'm going to state this without proof, so that you can derive this mathematically and you can show this actually. But so this turns out to be a very important result. If the discrete log problem is going to be infeasible over carefully chosen elliptic curve groups, then well, that opens the door to doing key exchange, encryption, decryption, and so on. So let us see whether we can get to that. So before that, I just want to point out that for the purpose of cryptography, the 2 curves of interest are not elliptic curves over reals, because those are infinite groups, but elliptic curves over finite fields like ZP, the so-called prime field, and the so-called binary field. So we work with both of them, elliptic curves over prime fields and elliptic curves over binary fields. So just like we had derived the equations for addition, unary negation, addition, and doubling for elliptic curves over reals, the very same equations hold for elliptic curves over prime fields. And there's a slight modification for elliptic curves over binary fields. So very quickly, elliptic curve over the first field, the first finite field, which is the prime field. The formulas for addition are similar to those for ECs over reals, but all the operations, so exactly what we have seen before, the same arithmetic, but all the operations are, including inverses, are modulo p operations. The equation of the elliptic curve is also the same, y square is equal to x cube plus ax plus b mod p. The only thing is, now here we keep adding this mod p, and the constraint is that 4a cube plus 27b square, this is a misprint, it should be not equal to. So 4a cube plus 27b square is not equal to 0 mod p, just like one of the previous slides, the same equation with a not equal to sign included. So this is the elliptic curve, points that satisfy x and y that satisfies this equation for a pre-given coefficient a and a predetermined coefficient b, and of course the field is known. So some particular field that is very carefully chosen. So in practical problems in cryptography, elliptic curve cryptography, this p is a very large number, which is something like 200 bits at the very least. So around 200 bits, 300 bits, 400 bits, but much smaller than what you use in RSA. You use 1000, 2000 bits in RSA. Over here you use 200, 300, 400 bits. Another interesting thing is that the number of points on the elliptic curve is order p, where p is this thing, the size of the field. Okay, so with that little introduction to elliptic curve over prime fields, the next thing is elliptic curve over binary fields. So in this case, the equation is slightly different. Over there we had y square is equal to x cube plus ax plus b. Over here, in the case of elliptic curves over binary fields, the equation is y square, there's another term introduced, y square plus xy is equal to x cube, not ax but ax square in this case, ax square plus b. As usual, all of these coefficients and the coordinates of the point x and y, all of these are elements of this particular field. So once again, if you have got this looking thing, this stands for Galois field. The number of elements over here is 2 raised to m. It's always a power of 2. So 2 raised to m, and you can represent these elements, as I explained before some lectures ago, you can represent them as binary strings of length m. Okay, key exchange using elliptic curves. So this is the first application. So now that we know the mathematics behind elliptic curves, we know the equations at least, we can write programs to do all those operations. I can write a program to generate some of the points, or at least to check whether a particular point belongs to an elliptic curve. I can write down a program to find the negative of a point, to add 2 points,